The other thing we're going to talk about here is the friction coefficient. Down here in the right-hand corner, there's a friction coefficient that dictates what amount of drag that we're using in this system, or the amount of drag that's been calculated in this particular system. There are various components that make up the drag in our system, or that defines the energy efficiency of our system. We have 6 components defined here, and depending on the methodology that is selected, these may be addressed differently. There's basically 4 main resistances that make up the F, or friction coefficient, in the lower right-hand corner of belt analyst. There are idler drag, which is the bearings in the idler, bearings and seals. There's alignment, that's how well the idlers are aligned angularly, transversely to the belt travel direction. There's rubber indentation, number 3 here, which is the idler roll that indents in the rubber as the belt's being pulled across them. There's material and belt flexure due to belt sag between the idlers. Those 4 items make up what we consider to be F, or the main resistances of the system. Then we also have miscellaneous resistances, miscellaneous drags, which is belt cleaners and plows and the pulleys and things that are point loads on the system. That's a separate category. And then we also have lift, which is just the gravity. It's overcoming gravity. If we have to lift material 100 meters, we have to overcome gravity of that. If we're lowering it, then gravity helps us. It's pushing us down. So lift is a separate item. The miscellaneous resistances are a separate item. But what we're going to talk about here really is the main resistances that make up what we consider to be our F coefficient. There are 4 methods of calculating F, our friction coefficient, in Belt Analyst. And in the old program, which you might still be using, you go to options and select friction methodology to pick up these different methods. In the new version, you can get it from the main taskbar here. You can see we've selected the SEMA Universal Method, which is a Conveyor Equipment Manufacturers Association of North America. Universal Method was published in 2005, which is the 6th edition. And in this case, it generates an F coefficient in this conveyor of 0.0242. If I select a different methodology, which is the SEMA 5th edition, which is all prior to 2005, you see a F coefficient is a little higher. It's calculated at 0.029, just a different method of calculation of the F. We also have a DIN 22101 in the DIN methodology, which is a German national standard. It's a little different. Instead of the program calculating an F, the user inputs an F. So you can input a 0.02 on the carry side, and perhaps you want to use a smaller number, 0.01. Excuse me, I put in a wrong number. I might select 0.015 on the carry side, on the return side. And then those actual numbers are used, and the composite F, which is a combination of carry the return in this case, is 0.0192. I can also select what we call a modified DIN, which allows you to input a friction coefficient and then adjust that based on speed and temperature to get the actual F coefficient. And in this case, it comes to 0.018. So we have various methods, and you can decide which method you would prefer to use. We recommend the SEMA Universal Method, which is the most complete method in our eyes and the most accurate. But if you prefer one of the others, you can certainly use them. So is this 024, is this a good number? Is this a correct number? How do we evaluate that number? First thing I'm going to do is I'll take you to the DIN 2201 specification so we can look at some of the numbers that the German standard. So I've brought you over to a table from some of our resource material, which is taken right from the DIN 22101 standard. And you'll see here, because DIN does require that the user select a number, it provides recommendations based on certain conditions. Therefore, if you have a very favorable conveyor, a good maintenance, low internal resistant material, easily rotating idlers, you might use an 017. a normal installation, let's say typical maintenance and typical installation might be around O2. Unfavorable conditions might be low temperatures, cold days, poor maintenance, etc. Your numbers may be O23 to O27. And if you have a regenerative conveyor, which is now we want to underestimate the friction requirements, since the friction is actually holding the system back, which is we want to underestimate now. It might be 012 to 016. These numbers are generally for, they've put in here typical conditions of a belt speed of 5 meters per second and a temperature plus 20. And then here's some multipliers as we use in our adjusted DIM calculations to increase or decrease those numbers depending on belt speed or temperature. So over time, as a user, you'll start to become more aware of these numbers and be able to look at these numbers and tell if it's in the ballpark or if your system is poorly inefficient or very good efficiency. In the program, there's another place here we're going to point out where we can actually look at these numbers and see if there's something we can do to improve them. Under the Drive tab and the Summary Data sub-tab, you can see here that the total friction is calculated 64.9 kilonewtons. The total lift force here in this condition is 39.18 kilonewtons. There's our miscellaneous drag of all of our skirting and plows and cleaners and pulleys, etc. And then our main resistances are now divided into the 4 pieces that we mentioned earlier. There's the idlers, belt indentation, alignment, and miscellaneous drag. And we can look at this now and we can determine if there's any of these that we need to pay more attention to. In this case, more than half of the resistance in this system, the friction in this system, is idlers due to the idler bearings and drag. So it would indicate that we should probably pay more attention to that and make sure that our idler drag and resistance is accurate. So if I come over to the idler drag, I can now look into this a little bit more closely. These are the numbers. The seal drag numbers are the important numbers in the idler calculation that we just looked at. And are these correct? So we certainly need, in this case, if idler resistance is this big a portion of our drag, we need to make sure that these are the correct numbers, and that means going back to our manufacturer and checking to see if these numbers are correct. If I put in a 0.7 here instead of the 0.9, you can see that our coefficient of friction drops fairly significantly to 0.021. And if I put in a bigger number, it goes up to 0.28. Anytime I can just blank out these numbers, I'll just hit the backspace and blank them out, and anytime they'll go back to the default values in the tables. In this case, it's important enough, it's a big enough number that we want to make sure these are correct. The alignment also is an important number that shows up in the idler tab. And angular installation tolerance, we have a 12 millimeter installation tolerance. If we assumed we have very good installation tolerances in our system, you can see the F value again drops down to 0.21, and conversely, if we made those bigger, that number would go back up again. The other value here that you have some control over is belt indentation. Not all of the calculation methods in the program look at rubber indentation, but the SEMA Universal method does. It does look at the cover gauge, the bottom cover gauge of the rubber, the idler roll diameter, and the speed to calculate idler rubber resistance. We are using SEMA defaults at this point, and we kind of recommend that you stay with this. If at any time you want to evaluate using a smaller belt deformation number or a more energy efficient rubber, you could contact us and we can provide you a paper, or there is a paper on our support site that you can download and read about how this is done. So the two things here that we've gone over, the loading conditions and the friction coefficient, what we really want to do is end up with a range of possibilities. We'd like to do a worst case loading condition with say inclines loaded only, and we want we'd want to make sure we had our lowest cold temperature condition, because cold temperature is higher resistance. We want to make sure we are on the high end of our alignment and the high end of our seal drag, and we may end up with a very big F, which is mostly due to in this case the cold temperature condition. But we may end up with a very big F that we want to, when we want to overestimate the F so that we make sure we have enough horsepower to start the conveyor. Conversely, we want to make sure we can handle the other condition, which in this case is declines loaded only, and the conveyor can actually be regenerative. And you can see here in our power tab that we actually have a negative power, and the brakes might even be required to stop the conveyor. In this case, we want to make sure we estimate a nice warm day, because we want to make sure the friction is low as possible, and so we might want to underestimate the alignment and assume it's very well aligned. We might want to underestimate the idler drag, and we may end up with a coefficient of friction down as low as 0.01. And then when we size our brakes, we'll make sure we have plenty of brakes to adequately stop the conveyor during any condition. So that's pretty much the end of our little program today of evaluating results, in particular loading conditions and friction coefficients. We recommend that whenever possible that you look at a wide range of conditions, both high friction conditions and low friction conditions, and low power loading conditions and high power loading conditions, and make sure that all the components are proper for the full range of loading conditions.